Okay, so this is the week when we really jump into some serious content here, and of course beginning with the science. There's a lot to learn, and the purpose of these lectures, of my lectures and these videos, is to give you a clear outline of the most important pieces that you need to keep track of. So I'm going to pull out some of the main issues from the Richard Alley reading, also make some reference to the lecture that you'll be seeing for Wednesday's class and also the virtual field trip on Friday, so that you have an idea of what pieces of this you must keep track of. Our purpose this week is to talk about fossil fuels and energy. We want to start off looking at energy usage in the US, especially here in Pennsylvania, and to be able to differentiate between fossil fuels and other kinds of fuels, other forms of energy. And then we're going to talk a little bit about climate change impacts. And this is going to anticipate a little bit of Richard Alley's lecture for Wednesday, which, as you'll see, is full of detailed information. So, to review just a bit, what we did last week was to think about our own feelings and our values when it comes to climate change, to be able to understand and explain the power of framing the issues of climate change, and to think about how scientists and politicians and other people consider this issue and the way that they frame it and the power that that has over what we think is important regarding climate change. All of this is part of preparing you for what I call the ethical process. We have to start with the science, because when it comes to ethics, I like to say that facts are your friends. We have to be able to agree with one another what it is that we're talking about. And so the factual basis for science, the very question of what is a fact and how do we know about the truth of things, all of that is fundamental to any discussion of what do we do about it. So if we can agree on the facts, that provides a common basis for discussion. And it's in that process of discussing that we learn what the ethical thing is to do. Along with this is the history of ideas and debates. Fact is that you are coming into a conversation that's been going on for decades. We see that there are already different communities, different individuals who have their commitments. The fossil fuel industry, for example, is one powerful voice, and environmentalists are another powerful voice. We want to bring as many different voices and as many different communities in this discussion as possible. And most important is that this should help you craft your message, for you to know where you stand on these issues, what your values are, how you can participate in a debate that's going to be shaping up, especially now over the next couple of years, but certainly over the course of your lifetimes. So therefore, you have to have a sense of yourself. What are you doing in the room? What is important to you? What do you need to get across? These questions are hard questions to ask, and we don't often explore these sorts of questions in the science classroom. We do a lot more of this in humanities. Science tends to think that the individual interaction with the science is negligible. It doesn't matter if you're a Republican or Democrat. You're going to address the material the same way. Whereas in the humanities, we often think of the importance of the individual, of the self, and how they read a text and what it is they see as being important. I think we'll see when it comes to climate change that these issues of who we are and what we bring into the class and what we think is important actually does change how we regard the materials. So we want to address both these issues, both the scientific, the factual basis, and also that process of interpretation. Again, we'll have a lot of time to talk about ethics later in the semester, but I want you to understand the role of science in preparing ourselves for this ethical process. So, what are our objectives for this week? We should learn the history of energy usage in Pennsylvania and be able to differentiate fossil fuels from other fuels. Pretty straightforward, but there's a lot to this. You'll see here on the slide that I've got the Pennsylvania furnace. I think you may have passed this building by on your way into State College from time to time. Now we get to find out what it's all about. So by the end of the week, I want you to be able to answer these questions about the Richard Alley reading in particular. How is charcoal made? What's the difference between charcoal and coal? When and where was oil first discovered? And what does Alley mean when he says that the discovery of oil saved the whales? Alley also talks about the history of First Nations people in modifying their landscape. So this raises the question for us about nature. Is there such a thing as the natural world? Or are humans always in the process of modifying the world? And then finally, what does Alley mean when he says that 85% of our energy is unsustainable? Now, as we've seen, Alley talks a lot about energy, and that shows us the way that he frames the climate change debate. And this week we're going to draw that out a little bit and see how those values resonate in his lecture and the way that he presents his material in his book. So, just to recap, what we're doing for Monday is a discussion that's going to be breaking down into your breakout sessions, and this is going to be an opportunity to hear what your colleagues have said in their first response paper. Then on Wednesday we have a webinar with Richard Alley. I'm going to emphasize this a couple of times. It's a webinar. It's a different URL than our normal Zoom classroom, so please pay attention to how you tie in to the class on Wednesday. On Friday, there will be no Zoom class. You'll be doing a virtual field trip, and all that's laid out for you on Canvas. So, let's get started and thinking a little bit more about fossil fuels and non-fossil fuels. By taking us back in history a little bit and talking about fire, discovery of fire and cooking and all these things, Alley is suggesting to us that human beings are energy users. That's a way to define what it means to be a human being. And of course, a lot of this had to do with the development of fire and civilization going back in time. But what we can see here in our own area of central Pennsylvania is the role of energy in the developing iron industry. And that's what the iron furnace is. And three things, as I'll emphasize again on Friday, three things go into the iron furnace, right? Iron ore, limestone, and charcoal. We're interested actually in all of these, but that charcoal is what's important here. That process of making charcoal had a significant impact on the environment in terms of deforestation. But also the process of simply dumping out the slag, the products, the byproducts that came from the production of iron into the environment. That's also a process of environmental damage that comes from this sort of industry. In this, Alley suggests to us that until the 1900s, virtually all of our energy usage was renewable. So charcoal is then a renewable resource. It's not a fossil fuel because charcoal is made from trees, and trees can be planted again, and within 70, 100, 150 years, chopped down and made into more charcoal. So that's a short-term carbon cycle. It goes back around again. In a way, whales are also a renewable resource. Seems like a weird thing to say. But as long as you don't overhunt the whales, which we have done, and arguably are still doing today, as long as you don't overhunt the whales, they will produce more whales, and we can extract more oil from the whales and use that oil then for various things. Wind power, water power were all things that were available before the 20th century. And in fact, train engines would start to run then on not charcoal. They could run a train engine on charcoal. You're running it on coal. And the use of coal in trains and steamships, beginning already in the 19th century and rapidly ramping up in the 20th century, that then begins our development of a fossil fuel industry. So if you look at this graph, you'll see that all the way back even to 1850, you can note some fossil fuel use. With the very first coal mines being opened up, the very first oil wells in the 19th century, right here in Pennsylvania. And then slowly around 1900, you see this ramping up. And in this graph, you've got coal and petroleum and natural gas all separated out from one another. Note that the production of cement and natural gas really doesn't begin at all until after 1950. And it's really there at 1950, the World War II and the end of World War II, with the explosion of the consumer economy, that we see this rapid expansion of fossil fuel usage. And look at those numbers in terms of cars. Only 27 million cars were registered in 1940. That's a tenth of what's registered a couple of years ago here in the United States. The presumption is that everybody has a car. Every family has a couple of cars. And that was not the case previous to 1950. It's not that long ago. It may seem forever to you, but 1950, I was born in 1962, so 1950 is certainly within a lifetime of a human being to see this rapid change in the way that we produce energy in that time. Now, briefly looking ahead to the next 20 years or so. So what do we see in the near-term future in terms of emissions and fossil fuels? Of course, the very best case scenario is that we simply stop using fossil fuels. We immediately transform our energy sector over into renewables, and that this rapid transformation of our society will result in the capping of warming to about 1.5 degrees Celsius. What's important to understand is even at 1.5 degrees Celsius, we still have some harms. The increased numbers of droughts and wildfires, the increased crazy rainfall events that we've had in the last decade, all of that is baked in. That doesn't go away just because we stop producing fossil fuels. So this is the very best case scenario. There's a worst case scenario. And the worst case scenario is what's often called the business as usual proposition, where we simply keep developing and increasing our use of fossil fuels. That we do not depend on renewable energy. And in fact, the World Energy Association predicts that at current rates, by 2070, the world will only be using 20% of its energy from renewable sources. So this business as usual scenario, even with a gradual transformation to solar that we see in some sectors and to wind, even with a gradual transformation, we're still going to be burning a lot of oil, natural gas, and coal. And so scientists project that the increase in temperature could be 4 degrees Celsius or more. In the short term, this means that sea levels will rise about 4 feet. So those of you who like to go on vacation to, say, the Jersey Shore, not Jersey Shore, Pennsylvania, the actual Jersey Shore, or to barrier islands off in Cancun or down in Florida, those will disappear. A 4-foot sea level rise will take those islands right out. And there are even more dire circumstances for river delta communities, such as the Nile River Delta in Egypt, or the river deltas in Bangladesh and Vietnam, where hundreds of millions of people live and where the land is very low, very close to sea level. That means that this disruption will result in massive climate migrations. Those people can no longer inhabit those lands and they will move slowly with the rising sea level. Really difficult to understand, and this is part of what we're talking about in terms of timescales, is that we can look ahead to 100 years from now and see about maybe 6 feet of sea level rise. But if we look ahead 500 years from now, we're going to see a much greater level of sea rise. And that's because what we do now will affect the future for hundreds and in fact thousands of years. So the worst case scenario is something we really want to avoid. And in fact, we are the only ones who can not burn that carbon dioxide in order to see that that happens. Now, in this graph, you can see they sketched out a couple of these different scenarios. And once again, that green line, which is a basic complete reduction or complete transformation of our energy system, that still does not bring the temperatures down. That the temperatures will remain elevated for some time to come. And then you have that business as usual scenario in the red, moving much, much higher. Again, the increase keeps increasing over hundreds of years. So, it's time for us then to talk a little bit about time scales. Because the fact is that these issues of time are really hard to understand. Now, one of the things you'll see is that Richard Alley talks about economics, the pure rate of time preference, and the fact that economists think about time in terms of 30 years at most. 30 years is an interesting number because 30 years is also the amount of time we generally think of as climate. So weather is day to day, and weather and climate are not the same thing. The fact that it's warm a day in January does not mean that the whole climate is changing. The fact that it's suddenly cold on a day in July does not mean that the climate is changing. Climate is rather that overall structure of the world's temperature, and then weather varies a great deal within that structure. 30 years, then, is this very human sort of time number. 30 years, about half of my lifetime. I certainly remember that the world was a lot colder when I was younger, and I grew up outside of Buffalo, New York, a lot more snow back then compared to now. And lakes and rivers would freeze in the winter in a way that I still remember in my own lifetime. Lakes and rivers that no longer freeze around here in central Pennsylvania. This 30 years, however, in terms of the kind of time that Richard Alley is talking about, the kind of time that we're discussing with climate change, is actually a very small aspect and a very small part of the picture. At the most, then, we have this human timescale of 70 years. And again, we can see this rapid change within a human timescale of the amount of CO2 that we've produced and the amount of fossil fuels that we've used over the course of my lifetime. That number is continuing to go up, and as you see, it's in fact rising exponentially. Even though things have leveled off here in the United States, many countries in Africa and Asia are now only starting to develop their fossil fuel industries. And so their increase also is adding to this overall larger increase. The most we can talk about in terms of a human timescale is about 7,000 years. You'll in fact note that what we call young Earth creationists believe that the world was created about 7,000 years ago. The Hebrew calendar, which is the calendar of Judaism, goes back about 6,000 years. So this notion of when God began to create the world that we hear about in Genesis, what we're talking about is the beginning of human civilization. Pyramids and aqueducts and Roman Colosseums and all of those trappings of the earliest human civilizations are only a couple thousand years old. There wasn't writing before 7,000 years ago. There wasn't any kind of city building before 7,000 years ago. There was very rudimentary agriculture compared to what we have now. That 7,000 years is a small fraction of time when we talk about Earth and we talk about what we can know about Earth's climate. As we'll be discussing, I think next week already in class, we can sample ice cores and know with a great deal of accuracy what Earth's atmosphere is like 400,000 years ago. In some cases, more than 1 million years ago, by sampling those tiny bubbles of air that are trapped in these ice sheets that we find in places like Antarctica and Greenland. These are ice sheets that are in fact more than 1 mile thick, almost 2 miles in some places, where snows stack upon one another over the course of thousands, hundreds of thousands, millions of years. And that provides a record for us of, among other things, what the atmosphere was like. So we know that there's only been a certain amount of carbon dioxide in the atmosphere over these last 2 million years, and that the amount of carbon dioxide we're putting in the atmosphere now changes the atmosphere in a way it has not been changed for hundreds of thousands of years. But even that is just a fraction of what we can know from geologic time. Now we're talking about not hundreds of thousands of years, but millions of years ago. Richard Alley is going to talk about sampling sediments in the ocean floor, going back tens of millions of years ago. This becomes very difficult, right? I might live 70 years. The human civilization might be 7,000 years old. We go back with ice cores to hundreds of thousands of years. Geologic time in these samplings of these ocean sediments goes back tens of millions of years. And yet, we know that life on Earth is more than 500 million years old. About 500 million years ago is when we had what we call the Precambrian explosion, a seeming explosion of life on the ocean floor that also changed the atmosphere, as we'll see. That explosion of life on the ocean floor created animals that had shells, and their shells formed the limestone over hundreds of millions of years that then is used in the iron furnaces here in central Pennsylvania. So in a way, limestone is also a fossil fuel. Maybe not a fuel per se, but it's a fossil product that was laid down hundreds of millions of years ago. The charcoal that we burn is hundreds of millions of years old. And so this is what Richard Alley means when he says that we are literally burning fossil fuels 1 million times faster than they were created by nature, or that nature could possibly create them now. That relationship is what's important here, because these animals and these plants were slowly extracting carbon dioxide out of the atmosphere over this long period of time, changing the makeup of the atmosphere, and now, suddenly, in a blink of an eye, when it comes to geologic time, we're tossing that carbon dioxide back into the atmosphere. We're not changing it anywhere near as much as those creatures did over hundreds of millions of years ago. The carbon dioxide concentration was perhaps 5,000 parts per million, whereas today it's about 415 parts per million. So we're not getting back all the way there, but in fact it's that change from a historical average of about 200 parts per million over the last 2 million years up to now 400 parts per million. That's the change, that rapid change, that makes climate change such a distressing and disturbing part of the world today. So if you look at this chart, you'll see then laid out here the history of the world going back 600 million years. Remember, the Earth itself is 4.5 billion years, right? So it's even that's only a fraction of this. But look where it says 100. So that's 100 million years ago. And if you divide that small space between 0 and 100 into 100 slices, then you'll go back a million years ago. And that tiny slice, 1/100th of that little space there, is the age of those ice cores. If we expanded that million years then out to the full length of this table, and then we split that million years up into 1,000 segments. Can you imagine that? You go back 7 of those segments, 7 of those 1,000 segments, and that's human civilization. So timescales, when we talk about geologic time, are very hard to keep in mind. When we look at the changes that we see back in these ocean sediments and other ways that we can know about this ancient past, we see a vast change in climate in Earth's history. That is certainly true. But when we're talking about climate in a human timescale, then these rapid changes would literally mean the end of human civilization as we know. So now take a look at this chart and note the way that carbon dioxide has fluctuated over the course of 800,000 years between about 180 and 280 parts per million. And that temperature also has fluctuated between those times. Those fluctuations, as we'll be discussing in a couple of weeks, have largely to do with Earth's orbit and changes in the Sun and the Earth's relationship to one another. And those roughly accord with the different ages of glaciers and the ice ages that we've had in Earth's past, and then periods of warming. Now again, this scale is 100, 200, 300, 400,000 years ago. If we look back to a human size scale, so again, something more that we can think about, not 100,000 years ago, but rather 10,000 years ago, so just that last tenth of that last segment. Here now we can see that over the last 10,000 years there hasn't been fluctuation like that, because we're taking that up and down, we're stretching it out to approximately human civilization. And what we see is for the whole of human civilization, we have had an atmospheric concentration of carbon dioxide at about 260, 270 parts per million. It is only in the very recent past then that that concentration has jumped up radically. Scientists have a pretty good idea of what's going to happen because of that rapid change in the atmospheric concentration, but to be perfectly honest, this has never happened before in human history. It's almost never happened before in terms of geologic history. And so that's why our projections of what will happen in the future are in ranges. We have an idea of what might be the future, but we can't entirely know for certain. So, how do we know what we know? And why should you trust what I'm telling you right now? In fact, I don't want you to trust it, not just for my sake, Don't trust me, don't trust Richard Alley, because we have PhDs and we're smart guys. You should be skeptical. Scientists are always skeptical about the facts. You should not believe in climate change. You should understand what the science is. And the fact is, there are really confusing claims about climate change. For instance, this idea that 30 years is climate. Well, as we've seen, 30 years tells us some things, but there have been rapid changes over the past 30 years. This 10,000 year scale tells us things that are quite different than just thinking about 30 years. The relationship between glaciers melting and sea level rise, also really confusing. There's been a lot of discussion and lots of reports about these giant icebergs breaking off of the ice shelves down in Antarctica. So it's disconcerting, but an ice shelf becoming an iceberg does not add anything to sea level rise. That's not the source of the concern. Rather, the concern is that those ice shelves breaking can release the glaciers behind them that are on land, and it's that ice from on land falling into the water and displacing water, that's the concern about sea level rise. I even heard from my nephew that he was worried about solar panels heating the earth because they're black and they absorb the sunlight. This is not the case because, in fact, the land around the solar panels also absorbs sunlight. And the difference between the way that the panels absorb the infrared rays and the land absorbs the infrared rays is not really that great. But these are the kinds of confusing things that come around. People have suggested that the recent war in Syria was caused by climate change. And while it may have been a factor, human activities like wars have many, many causes, and climate cannot be seen as the only one of them. So in this swirl of confusing claims, I'm going to try to help you to see some of the basic stories about climate change, some of the factual matters that then can help you get through what I call the website wars. And I know there is so much misinformation out there. So there are some good websites with positive information and factually, scientifically based information, but there's also websites that are out there with an attempt really to confuse you. Instead of taking these sorts of arguments, I want you to go directly to the science, to be able to understand enough about how scientists work and enough about what they're talking about in terms of chemistry and atmosphere, that you can understand the experiments that they're doing and the way that they're gathering their information. Much of the science of climate change is really very simple. And in fact, there are some basic experiments that you can undertake to prove to yourself some of the effects that we're talking about here in class. And then there's the process of science itself, which is really based on debunking ideas that people think might be true. Next week we'll read that Richard Alley talks about the National Academy of Sciences and why it was founded, and the way that scientists test one another through a process called peer review. He gives an example of power lines. And the fact is that people once were very worried about high transmission power lines causing cancer, things like leukemia, for example. Scientists took on this task and were able to prove that neighborhoods that had high rates of power lines in them did not, in fact, have high rates of leukemia or other cancers. And so in this process, science keeps building on itself, keeps learning more and more, debunks these false claims. So we want to learn about the science, and we also want to learn about something about science, about how scientists decide what information is true and what information is not. Now, looking ahead, just to recap for this week, we've got our discussion on Monday. The response papers, writers will be presenting their response papers to the rest of you in your research pods. And those of you who are not getting a paper have the job of listening and helping the presenter workshop their ideas, ask them questions, and try to work together to come up with questions and comments for Richard Alley in our webinar on Wednesday. And so Wednesday, again, is a webinar, not on the same Zoom call that we have our other classes. It's a different URL, so make sure you're signed up correctly for that. The presenters will be signed up as panelists, and so they will appear and be on video along with me and Dr. Alley, and so the 10 students and the 2 of us, there'll be 12 of us then in a panel to have a discussion with Dr. Alley. So again, for the rest of you, your job is to prepare these representatives from your research pod so that they have good questions and feel ready to engage Dr. Alley in a conversation about the science. The other 90 of you will be participants in this webinar. So your cameras won't be turned on, but you can ask questions by using the Q&A function in the webinar. So just click on that, type in your question. We'll be paying attention to that over the course of the webinar and try to get as many of those questions answered as possible. Then on Friday, there is no regular class, there is no Zoom class and no webinar. Rather, you have what I call a virtual field trip, a series of videos and interactive activities that I've created for you on Canvas. So look on Canvas for that virtual field trip. I want you to do it on Friday, but you needn't do it at any particular time, and there is an extra credit assignment for you to submit as part of that. I think you'll really enjoy it, and if any of you happen to be here in State College, or when you do get to campus, do stop by and have a look at that Center Furnace Mansion. I think you'll really enjoy it. So that's it for me for today. I look forward to discussing all this material with you in class and to seeing you all very soon.